This video is going to cover the entire 3.2 section in the textbook because we're not going to spend a ton of time on standard form, which is what this is about, as we did on vertex form. Vertex form, we really got into the details of a lot of different factors, but standard form specifically isn't as useful for things like graphing as vertex form was. So while we are going to see standard form for various things throughout the course, especially when we're looking at solving equations, for chapter 3, when we're mostly focused on graphing, standard form we're going to just kind of go through pretty quickly. So with that being the case, let's take a look. To start things off, let's just remember what standard form looks like. So it's y equals ax squared plus bx plus c. Those three parameters, a, b, and c, are all going to have some kind of effect on our function, just like a, p, and q did when we were looking at vertex form. So let's hop over to Desmos real quick and see if we can figure out what these do. So a, b, and c. All right, so first up, A. You may notice it's the same letter that we had at the start of our vertex form, and that is the case for a reason. Because if we move this around, you'll notice it does the exact same thing. It's the same letter for the reason. If you have a function written in both standard form and vertex form, they'll both have the same A values because they really do represent the exact same thing. So that's an easy one. A, I'm just going to say same as vertex form, which, if you've forgotten, is two things. It's our direction of opening, and it's our width or steepness or whatever you want to call it. B and C are a little different though. So you might think maybe B is related to Q or P in some way. It's not quite. So if we play with B, you'll notice that changing B really moves the entire parabola in a kind of weird way. So it's sliding around diagonally to the right now, focusing on the vertex, and then it's going back up and diagonally to the left. So B is kind of unpredictable and not really helpful. So if we hop back over here, we can say that B moves the graph horizontally and vertically, but really in a way that we're never going to be able to use in any effective way. Which is really the main reason why we don't often graph in standard form. The other reason we often don't graph in standard form is we don't know where to start, right? Vertex form gives you the vertex, so it's easy to know kind of where to begin and structure your graph, but standard form you don't have as much of an idea. All right, going back and looking at C, if I change C, keep an eye on the graph and see what it does. We can see that it is moving up and down. So this is a lot like Q in our vertex form, except it doesn't give us the vertex. If you pay attention to the graph, let me make our numbers a little bit easier here. Let's go with, we'll say 3. Okay, pay attention to that -1 value and look at what that corresponds to on the graph as I change it. So now C is -3, now it's +2. And so if you pay attention, hopefully you'll have noticed that that C value gives us our y-intercept. Right? So right now, my C value is 2, and my y-intercept is 2. And that's going to be the case for this. So C does two things for us. It moves the graph vertically, up and down, and it also tells us the y-intercept. The only downside to that is, unlike when we were doing lines in slope-intercept form in grade 10, we don't really care about the y-intercept when it comes to parabolas too much, only when we're dealing with sort of specific word problems. Otherwise, the y-intercept is just kind of a curiosity. It can kind of help you graph. It is a point, so if you're in standard form and you see that y-intercept, that does tell you something about your graph, but it's just not all that useful on its own. So our main focus of this video is actually just going to be doing a quick conversion and seeing if we did have something in vertex form that we did want in standard form for some reason, how would we affect that change? So how do we go from vertex to standard form? And that's going to be a fairly simple process that just relies on some skills that you already have. Right, so let's start off with a pretty basic one. We're going to convert y equals x plus 4 squared to standard form. So this is in vertex form. It's missing an a value, it's just 1. It's missing a q value, which is just 0. But it is in vertex form. We've got that bracket with the square on it, which is kind of what we're looking for. So remember, it's y equals ax squared plus bx plus c. This is what we want to end up with. So if you compare that to what we have right now, and think about what you need to accomplish, well, the biggest issue is those brackets. Standard form's got no brackets in it. So if we're going to make this conversion, we got to get rid of those. And that's really going to be our first step. So thinking back to grade 10, if you think x plus 4 squared, well, a square represents multiplying something by itself. And so that's what we're going to do. We're going to multiply out the brackets and get rid of the exponents. Once we've done that, we just have to simplify, and then we're basically done, at least for this one. So y equals x plus 4 squared is the same thing as x plus 4 times x plus 4. And then looking at that, that is something that's easy to mess up, and it is something you would have spent a lot of time learning in Math 10. So remember, when you're multiplying a binomial times a binomial like this, there is a specific strategy learned with a specific memory tool, which was FOIL. Running you through what FOIL stands for real quick. F is for first, where we multiply the first term in each set of brackets. O is for outside, which is the farthest left and the farthest right, so that's x and 4 in this case. I is for inside, where you multiply the two in the middle of this little setup here, so 4 and x. And then L is for last, which is the last term in each set of brackets, which is 4 and 4 here. Really what ends up happening is it's just everything in the first polynomial times everything in the second polynomial. So x times x times 4, 4 times x, and 4 times 4. Which gives us this. So x times x, 4 times x, 4 times x, and 4 times 4. Not necessary at all to blow it up this way, but just as a refresher, this is what it looks like. So x times x gets me x squared. 4 times x is 4x, and then another 4x. And then, remember, 4 times 4 is not 8, it is 16. And then the last thing we can do here is we can just simplify these two 4x's together, so we can combine some like terms. And we've got x squared plus 8x plus 16. And there we are. So since we didn't have an a value or a q value to deal with, this one is now in standard form. It's finished. We've done everything we can. So let's give another one a shot. So y equals 2 times x minus 3 squared plus 1. So same process. First thing we need to do is get rid of the brackets. I'm just going to hop off to the side here to do this so I don't have to write out the whole thing again. So x minus 3 times x minus 3. If I FOIL that, doing x times x times 3, 3 times x, 3 times 3, which will get me x squared minus 3x again, and plus 9, or x squared minus 6x plus 9. So if we go back to our question and we just plug that back in, we've got y equals 2 times x squared minus 6x plus 9, and then plus 1. Now this one's a little bit more complicated because we do have an a value and we do have a q value. So just thinking bedmass, we've dealt with the exponents. The next thing we need to deal with is this multiplication of the 2 by everything in the brackets. And to do that, we need to distribute. So remember, the 2 on the outside gets multiplied with everything on the inside. It's like foiling, just a little bit simpler. So we've got 2 times x squared, which is 2x squared. We've got 2 times negative 6x, negative 12x, and 2 times 9 gets me 18. And then we still have that plus 1 at the end. And then our last little thing here is we do have two like terms in the 18 and the 1. So if we put those together, we've got y equals 2x squared minus 12x plus 19. And this is standard form. All right, so now we could use this maybe to solve an equation or to combine with something else or who knows what. All right, so trying one more. I'll give you one to give a shot on your own. So we've got y equals, and just to make it a little bit harder, we're going to throw a fraction in there. So we've got negative 1 over 5 x minus 7 squared plus 10 over 3. So go ahead, pause this one here, give it a shot for yourself. The fraction is going to make this a little bit confusing possibly, but see how you do. Come back once you're done, and we'll see how it goes. All right, so we're going to follow the same process here. So if I do x minus 7 squared, I'm going to get x squared minus 14x, right, from negative 7 and negative 7, and then plus 49 from negative 7 times negative 7. Still plus 10 over 3. Then I need to distribute. So this negative 1 over 5 is going to get multiplied through with all three of those. So I've got negative 1 over 5 x squared plus 14 over 5x minus 49 over 5 plus 10 over 3. Then the last thing we need to do here is combine these two at the end, but this one's a little bit tougher than it was on the last one we did because we got the fractions to deal with. So if we're looking at negative 49 over 5 plus 10 over 3, we need a common denominator for those, which in this case is going to be 15. So we're going to multiply the first fraction by 3, second one by 5. Gets me negative 147 over 15 plus 50 over 15. And when you put those together and slot them back into the question with the rest of the equation, we've got negative 1 over 5 x squared plus 14 over 5x minus 97 over 15. And there we go. It's in a pretty ugly looking standard form, but it is in standard form. And that kind of wraps up how to convert vertex form to standard form. Don't leave just yet, though, because there's one more thing I did want to go over. Just something that's going to pop up throughout this course, really, but also specifically throughout this section a lot, is something you would have learned hopefully in the past, which is function notation. I'm not going to do a super deep dive into this, so if you do need some help with this, maybe check in with me, or if I'm not your teacher, check in with your teacher on how to do function notation if you don't have a really good handle on it. But just to give you an idea, function notation, when it's written out, especially with a quadratic, is going to look something like this. Where this thing up at the front, the f bracket x bracket, is, we call that f of x. And it's just talking about a function, some kind of function, that's based off of x as its variable. And we can see the x over here. So this x and this x are the same. F of x really, honestly, is just the equivalent of y. It's just it's a representation of the value of the function. It's just written in a different way that really emphasizes the fact that we're putting something into this function and getting something out. So to exemplify that with maybe a more real-world application, if you ever end up taking Physics 11 or if you're just into sciences, you might see a function that looks more like this. So this we would say is h of t equals negative 4.9, yada, yada, yada. So that h of t at the front, what that is representing to us is the height, right? So h is going to be height most of the time. And it's height at a specific time, whatever t represents. So height at time t. And so we can use that to communicate different things. Like say I wanted you to find the height at 2 seconds. I might just write h of 2. That is the height when t is 2. And so we can use function notation to combine things. We can use it to communicate things. And it's just useful for a lot of different contexts. So expect to run into that pretty frequently as you're going through this course and as you move really onto any sort of upper level math or upper level science classes. So one last thing, using function notation, but also just kind of refreshing some skills. I'm just going to throw a word problem into here for you to try out quickly. So we've got the cost of some kind of product. Doesn't really matter what. can be modeled with a specific function which is c of t, so that's cost after a specific time, equals negative 0.25 times t minus 6 squared plus 103.5. And so t is the number of months since this thing came out. I could ask you lots of different questions about this, but just a couple of really quick ones that don't require any deep thought. I might ask you something along the lines of, what is the maximum price of this product? So what's the most expensive it will ever be? So pause here real quick, see if you can figure it out on your own. Learning how to interpret questions like this is a really important skill. Okay, so when we're looking at maximum price, a really good idea is just to kind of maybe sketch this out real quick. So t minus 6 squared plus 103.5, our vertex is going to be at, well, 6 and 103.5, which will be somewhere here. We know the graph is going down. It's going to look something like this. Specifics don't really matter. What does matter is the fact that we want the maximum price. And that word, maximum, really should trigger something in your brain, because we talked about maximum values back when we were thinking about just the basic characteristics of parabolas. And your maximum value is either going to be infinity, which it's definitely not here, or it's going to be your vertex, which is exactly what it is. It's the highest point on the graph. And so for us, our maximum value, pretty straightforward, is just 103.5. Follow-up to that would be something along the lines of, when does the cost peak? So when does it hit that maximum? And so if we look at this, that is going to be where we land at 6 months. And there's lots of other things you can say about this. We can talk about y-intercepts, we can talk about domain and range, but that kind of wraps up what we're looking at in terms of standard form. So in our next video, we're going to learn how to go from standard back to vertex form, like if we wanted to draw some graphs.